Good morning. Today we will discuss about different techniques in fabrication of membranes in lecture 3 and lecture 5. And we try to introduce the famous fabrication method. There are many methods for fabrication of membranes, but some of them is more famous and more used. In this slide, you see the most used traditional methods. These methods have been used more than 100 years for fabrication of the mostly polymeric membranes. And we introduce these methods in this lecture. As you see, we have sintering, mostly used for ceramic membranes, nanofiber fabrication, track etching, stretching, and phase inversion. Phase inversion have been introduced by Loeb Soriradzan. Soriradzan was an Indian scientist that he lived in USA. And with help of Loeb from USA, introduced the phase inversion method that is a very simple method in comparison to other one for fabrication of the membranes. And with introducing this method with phase inversion about 70 years ago, the production of the membranes is very progressive, and the price of the membrane is reduced. This phase inversion can be categorized to 4 main categories. Thermal induced phase separation. Phase separation or phase inversion is the similar. Phase separation or phase inversion, thermally induced, named as TIPS. Vapor induced, VIPS. Evaporation induced, IPS, and non-solvent induced, NIPS. Okay? When I will say NIPS, that means non-solvent induced phase separation. The first technique, that's very old technique, is the stretching technique. In the stretching technique, we use semi-crystalline polymers. We use semi-crystalline polymers such as PTFE, polyethylene, polypropylene, and we usually melt, not dissolve in solvent. We usually melt these polymers, and after melting, we produce a film or a fiber, hollow fiber, okay? And when we coat this melted polymer on the surface of a glass, the polymers should be reduce the temperature. And with reducing the temperature, the polymer solution changes to solid, okay? And changing of this liquid phase to solid phase is named phase separation or phase inversion. Phase inverse from liquid to solid, okay? Therefore, in phase inversion or phase separation, we have a liquid phase. Liquid phase can be from melting or from dissolving in solvent, okay? We melt the polymer or we dissolve a polymer in the solvent. In stretching technique, we usually melt, or if we have a dissolved solution, the concentration of a polymer is very high. And we have a very viscous solution. We coat on a glass or on a support or produce as a hollow fiber. And when began to the solidification, we stretch the new solid films. In nanofiber, we stretch with these rolls, with speed of these rolls, and in the flat sheet, the support is separate together and close to the stretching of the film. When we stretch the film, as you see in this SEM image, when we stretch, the chains would like to separate from together and produce a free space. And this free space is pore membrane, and this area is the body of membrane, matrix of membrane. Therefore, with stretching, we produce some porosity in the semi-crystalline polymers. The porosity is very high, the flux is very high, the pore size is big. Therefore, these membranes mostly is microfiltration. We cannot produce nanofiltration with this method. In this method, we have a big pore size. The second technique is track etching technique. In track etching, with using of the high energy radiation, such as gamma radiation, we have a concentrated laser or gamma irradiation, and we focus the irradiation on the previously prepared the film. We have a solid film, but no porosity. We have a dense film, and we put this film under the high energy radiation, and with the radiation, because of the high energy, the chains of polymer is destroyed. We have a long chain of polymer. With irradiation, we chop these chains. Next, after irradiation, we put the membrane, the film, in etching bath. Etching bath is a solvent bath that can dissolve the irradiated area. With irradiation, the molecular weight of polymer reduces in the irradiation area, and this area can be dissolved in solvent, and other area cannot. Therefore, with irradiation, we destroy some of the polymers in this area, and this area can be easily dissolved in the solvent, and other area cannot, and therefore we produce pores. Here also the pores is big because we cannot very reduce the laser diameter. Mostly used for microfiltration, and we have a cylindrical pores. This is a special that we have a cylindrical pore we can reduce the pore size in microfiltration amount. We have 800 nanometers. We can reduce the size, and the pore size is narrow. The next day, I say that, the previous day, I say that the similar pore size is good from separation and fouling. In these membranes, we have usually the similar pore size, but you see that some cases to irradiation is near together, is close together, and cause to some big pores. But normally, all of the size is similar, and the fouling of these membranes is low comparison to the phase inversion. Usually, polycarbonate polymer, semicrystalline polymers used in this method. The third method, is sintering. Sintering mostly used for ceramic materials. In sintering, we usually have a powder, and with pressing the powder, we prepare a disc, a thin disc, prepared by high pressure pressing, but the stability of this disc, this film, is not suitable. And with a very low pressure, we can destroy and brittle this disc. For increasing of the stability, we should sinter the obtained pressed disc for attachment of the particle together. Sintering, that means we use high temperatures. For example, for alumina ceramic membrane, we use 1,700 centigrade. For silica, we have a need lower temperature, 1,200 centigrade. Therefore, we need high temperature for attachment and increasing the stability and strength of the membrane. In this method, we use powder of inorganic material or powder of polymer. We can also fabricate this disc with polymers. We put the polymers in the pressing and press the polymer and use low temperature in polymer sintering. In polymer sintering, we usually use 200 centigrades. But the resulted polymeric membrane is not good efficiency in this method, and we most usually for ceramic membrane fabrication. Also, we can fabricate the ceramic membranes as 2-layer, 3-layer, 4-layer. The commercial ceramic membranes usually have 3-layer, okay? And you see in the support layer, we have a big particles. The second layer have small particles. That means this small layer is selective layer, active layer, or separation layer, and these big particles act as a support for the thin layer. For both layers, we need to resintering. we first press and sinter the bottom layer. In the second step, we coat the second slurry on the surface of support, and again we re-sinter. Therefore, in the fabrication of ceramic membranes, we usually 3 or 4 sintering steps in high temperature, therefore need high energy production, and therefore the price of ceramic membranes is very high. By pressing of and sintering of this particle, between the particles, we can produce the pores. If the particle is small, the resulted pores is small. If the particle is big, the resulted pores will be big. With controlling of the size of powder, we can control the size of pores. Therefore, the sieving and meshing of the powder is important in ceramic membranes. Another process is electro-spun nanofiber membranes. We have a microfiber filters. Our microfibers used in cloths. We have a fiber with a diameter of 200 micrometers, 300 micrometers, 400 micrometers. This is a microfilter. Nano means that the diameter of fiber or particle should be less than 100 nanometers. In the definition of the nanotechnology, we say that every particle, every film, every fiber that have a dimension less than 100 nanometer, it is produced by nanotechnology technique. Okay? We have a microfiber filters. When we have a microfibers, the obtained pores between the fibers will be big, okay, and they will be filter, not membrane. For fabrication of the membrane, we must produce the fibers with very thin diameter, nanofiber, okay? But producing of the nanofiber from the needles that used in microfiber is very hard. And production of the needles with diameter of nanometer is very hard. And in the using of these needles, because there are some gels in polymer solution, the needles rapidly block it. But these gels, okay? In the preparation of polymeric solution, all of polymers not completely dissolved. Some of them not good dissolve and prepare the gels. The gel is particle. And these gels that we cannot see in the solution can block the needles, nanometric needles. For this reason, for reducing of the fiber diameter, electromagnetic is used. That means between the needle and the collector. Between the needle and the collector, we induce a very high voltage electrical field. And this high voltage stretch the microfiber to reduce the diameter. In this area, we have a microfiber produced. The produced microfiber between this distance, that usually 20 centimeters, this distance changed from microfiber to nanofiber with stretching by electric field. We prepare the polymeric solution, fill the syringe, and apply very low pressure for injection of the polymeric microfiber, and collector began to collect the fibers, and in this collecting, the microfiber changed to the nanofibers. And when we have the nanofibers, the free space between the nanofibers will be nano-size pore. And we can produce microfiltration, ultrafiltration, and nanofiltration with this method. Okay? The production of nanofiltration is very hard, but it is possible. We must control all of the parameters to reach the very nanofibers for production of nanofiltration membrane. We can easily prepare the MF and UF, but fabrication of nanofiber have some challenges. Usually, this system, collector and syringes, put in a chamber because we have a high voltage, and it can be dangerous. And we must use some equipment that do not conduct the electricity and should be isolated. This is you see, this is this device, the syringe and the pump for injection. This is collector. Collector can be vertical or can be horizontal. Both design, there is. You see this here. The high voltage. We can control the humidity of chamber. We can control the temperature. And I say that this distance between needle and collector usually between 10 to 30 centimeters. It is very low distance. In this distance, the liquid polymers should be changed to the solid fibers. Therefore, we must use the solvents with high volatile properties. That means the boiling point of the solvent should be low. Usually use mix of acetone with DMF, acetone THF, acetone NMP. Acetone, very rapid volatile. Therefore, usually mix of the acetone in this distance and with temperature, usually use 40 centigrade temperature in this chamber, and the produced nanofibers rapidly change from liquid to the solid state. The production in this method need high time, because we want to produce 100 micrometer thickness with nanofiber thickness, okay? We usually 2 hours need for production of a membrane with thickness of 100 micrometer. Therefore, we put the syringe with polymer and began the production and the nanofiber product, and 2 hours, 1/2 hour is needed for completing the membrane, and therefore this technique is time consuming, as is not rapid. In industrial scale, for increasing of the productivity and reducing the time, use many, many nozzles. In lab scale, we mostly used 3 or 4 needle, okay? But in the industrial, use 100 needles that simultaneously produce the nanofiber. But in industrial scale, we also need about 20 minutes for production of the membrane. But in the phase inversion, we need 1 minute. 1 minute, 20 minutes. It's very different. Therefore, phase inversion method is most industrial method because the production speed is very high. With the addition of any additive, any nanoparticles, any new monomers, new polymers to the polymeric solution of phase inversion or electrospin, we can produce for example, nano-composite membranes. In this paper, silver nanoparticles were added to the casting solution, to the dope solution, to liquid polymeric solution, and the produced nanofiber, you see, have different morphology, and the silver nanoparticles mixed and decorated on the fiber surface and cause to antibacterial properties to the membrane and reduce the biofouling of the membranes. But the most used industrial method is phase inversion or phase separation technique. As I said, in the phase separation, we first produce a liquid polymeric solution. And with change of this liquid solution to solid film, we produce the membranes. And the change from liquid to solid is named phase inversion or phase separation. Of this change from liquid to solid, mostly done with non-solvent, vapor, evaporation, or thermal. For technique, for change liquid to solid. Non-solvent polymer dissolve in a good solvent, but if the polymer is not dissolved in another solvent, the another solvent is non-solvent. Okay? Polymers is dissolved in organic solvents, like as dimethyl acetamide, dimethyl formamide, methylene prolidone, and others, but do not dissolve in water, okay? Do not dissolve in ethanol. Therefore, ethanol, water, is non-solvent for polymers. And when we add drops of polymer in the non-solvent, rapidly produce a circle particles. We use these methods for change of liquid to the solid films, and in this step, with control of conditions, we can produce porous or non-porous membranes. Both porous and non-porous can be produced. We can produce spongy membranes, finger-like membranes, and others. All of the membranes can be produced with phase inversion technique by controlling the conditions. In lab scale, for production of the thin film layer, we usually use this device. You see it, have a different configuration, structure. And we say applicator, doctor blade, or knife. In the papers, you see that say that I cast. This coating is called mostly casting. I cast the casting solution, the dope solution, the liquid polymeric solution on a glass or on a fabric using doctor blade with thickness of 200 micrometers. Okay? This device can coat the micrometer layers on a surface. Surface can be glass, fabric, or every plastic surface. Every surface we can coat the polymeric membranes, but we usually use glass, fabric, and plastic films. In this applicator, with this, we can control the thickness of the film coating. When we open, this area go to the up and the thickness increase. With closing, go to the bottom and reduce. But this device have a constant thickness. This have a 4 area, and each area have a distinct thickness. For example, the bottom is 100, the right is 200, top is 50, and the left is 150 micrometers. The use of this is easy, and the long time of use is high, but this may be destroyed and need to the repair. This is also have a 4 side, and every side is the specified thickness. For coating of the casting solution with these devices, we usually use this device. This device have a specific speed. We can control the speed of casting. We can cast with my hand, put the polymers, and cast with hand. But the speed of hand may be different from one person to another person. And this casting speed is important. Therefore, it is better we use a speed control casting. That we put this one here, put the polymers here, and we coat the layer on the membrane surface. We have a video, a possible play video. Video 1. This is my lab in Iran. My students want to prepare a flat sheet membrane with this device. The glass, this is the applicator. We prepared a casting solution, you see the viscosity is like the honey. With controlled speed here, we cast and rapidly transfer to the non-solvent. Non-solvent is water. Contacting with water, the polymer, the liquid thin layer, rapidly changes to the solid one. And after 30 seconds, the membrane is ready. During the phase inversion, in this step is very important, the solvent exists from the polymer, and instead of it, non-solvent go to the polymer solution. This existence and entrance produce the pores. The entrance of the non-solvent into the film layer cause to the pores, cause the porosity. The polymers do not like the water, and they want go out from the water. They do not like to close off the water, and therefore with inserting of the liquid polymeric membrane to non-solvent, they rapidly all of the chains want to get out from the water and collect together, and when collect the chains, then they will be solid. Liquid have a free movement, but when all can collect in one place, the change from liquid to the solid will happen. The general schematic of the membrane preparation, flat sheet one, shown in this slide, we must first prepare a dope solution or casting solution. For preparation of this solution, we need solvent and a polymer. A polymer that should be dissolved in solvent. This dissolving mostly need 1 day. After addition of polymer to solvent and mixing, usually we need 12 hours, but in the lab we use 24 1 day for completing dissolving and reducing of the gels. I say that some polymers cannot be dissolved and the gels. During this styling, maybe some air, some gases will be inserted in this solution, and this gas causes to the defect in the membrane, and during the fabrication we see that some pores, visible pores, there is in the film, and this due to the gases in the dope solution. Therefore, after complete dissolving, we 1 day again without stirring. Keep the solution for degassing, or use an oven for degassing. We close the dishes of the dope solution and put it in an oven for 6 hours in 50 centigrades. The high temperature reduces the solubility of gases in liquids. Okay? After 6 hours, we get out from the oven and began to fabricate the membrane on glass or fabric. And after the coating, we put them in the non-solvent. Organic solvent exists, and non-solvent enter to this layer, and this exchange between the solvent and non-solvent goes to the pores. The exchanging rate is very important, exchanging rate. If we have a high exchange rate, rapid entrance, rapid exit, we will have small pores. Rapid exchange, small pores. If we have a slow exchange rate, we will have a big pores. Okay? Therefore, with controlling of this speed, entrance and exit, that calls exchange rate, we can control the pore size of the membrane. We can produce microfiltration if there is slow exchange rate. For nanofiltration, we must increase the exchange rate. In industrial scale, I showed yesterday the film. This device is used. The process similar, but the device is different. In this case, in this area, we have a ductor blade and solution. By rotating of this roll, that on the surface of this roll, we have a fabric. Fabric come from the bottom of the ductor blade, and a thin layer of the polymeric solution coated on the fabric. In industrial membranes, we used fabric always, because a fabric increase the strength and stability of the layer. But in lab scale, no necessary for using of the non-woven fabric. After coating, rapidly go to the gel tank or coagulation tank or non-solvent tank. In this step, 10 seconds, the liquid film changes to the solid film and go to the rinse tank. In this rinse time, about 5 minutes, the membranes will be in the water for complete exchanging of solvent with non-solvent. All of the membrane pores produced and will be filled with water, with non-solvent. After that, they take off, rolling, collect the prepared membranes. We can control the non-solvent with temperature and other parameters for producing the good membrane. You see that the process is very easy. The process, we prepare a solution, cast, and in a non-solvent, we produced a membrane with high speed. But the controlling of conditions is very, very important. And we have a very errors. We prepare a similar solution, and I give this solution to 2 students. And each student prepare with the similar device, similar non-solvent, all is similar. only student is changed. And after fabrication of the membranes, one student flux is 100, the another one is 300. Many errors. You prepare a membrane, okay, one sheet, and cut 2 circles for testing. This circle is 100, this circle is 200 flux. In one sheet, all of methods, all of cells, every is similar. But the flux and rejection is different. It is the problem of the phase inversion. The phase inversion method is very good, but fabrication of a uniform membrane is very difficult. From one day to another day, the membrane is changed. Today, we have a high humidity, and tomorrow, low humidity. The humidity of the air in this casting is very important. The humidity is water, okay? Water is non-solvent. The humidity of the weather in this casting can cause pere-solidification. The humidity caused here during the casting caused the solidification. We cannot see, but happens. Therefore, the humidity, the temperature of air, and many parameters is important. The speed casting, one student rapid, one student slow, is very important. We have many errors, and therefore we must control these conditions. Please, video 2. Some companies can suggest their devices for fabrication of membranes. There are many videos in YouTube. You can see them. This is a device in lab scale for production of the membranes on the surface of the glass. This is a coagulation bath filled with non-solvent. That here is water. This device has software that controls the speed of the casting. This is the applicator which can change the thickness. You see the thickness is controlled with digital system, not with hand. Here also controlled with hand that show that our system can be digital controlled and with hand also. Casting solution. This chamber is oven and can control the temperature or can control the humidity. I discussed non-solvent and I mostly discussed about NIPS, non-solvent induced. The second method in phase inversion is EIPS, evaporation induced. In evaporation, after the coating, we do not use non-solvent and cause the obtained films in the contact with the weather or in an oven for evaporation of the solvent, okay? Evaporation phase inversion. In this evaporation, we have non-porous membrane. EIPS, evaporation induced, used for production of non-porous. For example, for protein exchange membrane. In the fuel cells, we have not used NIPS. We used EIPS, evaporation after the casting the films located in oven with control of humidity, control of temperature, and began to evaporation of the solvent. After evaporation, a solid layer will be produced that used in gas separation, in perovaporation, in exchange membrane. That in this type of membrane, we need non-porous membranes. These images is taken during the phase inversion with the microscope and photographer, okay? You see the time. I said that the phase inversion is very rapid phase. You see that during 2 seconds, the pores will be produced. In this area, okay, you see this boundary. This is a polymer solution. Here is water solution. When the water and polymer solution are contacted together, the water began to diffuse. Diffuse in the polymer solution, and in diffusing, produce the pores. You see the road of the diffusing, and this diffusing produce this finger-like pores. And in diffusing rate, our exchange rate is important. For example, in the right photographs, we have 3 different polymer solution. The polymer is similar, polyether ether ketone, but their concentration is 12, 10, and 8%. This, with increase of the polymer concentration, the viscosity of the solution increases. Therefore, the increase of viscosity reduces the diffusion speed. Therefore, you see in this area the similar time for low viscous solution, the pores is rapidly produced, but for the high viscous solution, the diffusion rate is low. Okay? Therefore, in these photographs, we can see the phase inversion process is very rapid, and the exchange rate that can be changed by solvent type, polymer type, temperature, polymer concentration, and many other properties that okay. There are 16 parameters should be controlled in fabrication of the phase inversion membranes. Phase inversion membrane can be fabricated as hollow, tubular, or flat sheet. No important. The mechanism is similar. Only the configuration of membrane is changed. We must control these 16 conditions. And with change of every of these conditions, the properties, the flux, the rejection of the membranes will be changed. We have a 3-step in the fabrication of the membranes with the NIPS method. We must prepare a casting solution, condition of film casting, or tube casting, or hollow fiber casting, and composition of the coagulation path. We prepare casting solution, cast, and cause and immerse in the non-solvent bath. We have 3 steps. And all of these 3 steps is important. We have a 3 temperature of casting solution, temperature of casting medium, and temperature of coagulation bath. We must control 3 temperature. And we know that with the change of temperature, the kinetic is changed, and the diffusion rate, exchange rate, can be influenced with temperature. Polymer type, with change of polysulfone to PVDF, the membrane is different. Polymer molecular weight, very important. Solvent type, concentration of the polymer. Additives, we can additives to the solution. Pore-former, we can add pore-former. We can add photocatalyst. We can add antibacterial agent and different type of additives. The thickness in the casting, the thickness is important. Humidity of medium, the casting speed, evaporation time in air. When we cast and put it to go to the coagulation bath, we have a 3, 4, 5, 6 seconds between casting and immersing in non-solvent. One student rapid in the 3 seconds, another student is slow and 10 seconds between the casting and immersion. Therefore, this contact with air is very important, and this is the main reason for change in flux with change with student. Support type, the glass, the plastic, the fabric is also influenced on the membrane flux. Usually, the membranes on the fabric support have higher flux from the glass. When you cast in the glass, flux is 200. When you cast in the non-fabric, 2 times, 3 times, the flux increases. And the type of the fabric, non-woven fabric, is also important. The non-woven fabric density, pore size is very important. In the coagulation bath, the non-solvent type added polymer solvent to bath. We can add 5% the solvent to the non-solvent. With addition of the solvent to the non-solvent, the exchange rate decreases. The exchange rate, when we add the solvent to the non-solvent, the non-solvent will be similar to the solvent, okay? When we add the solvent to the non-solvent properties of the water will be reduced. And this reduces the exchange rate, and the pore size of membrane will be increased. We can add additives to the bath and other properties. Therefore, phase inversion is a very easy method, but we must control all of these 16 conditions, and control of all conditions is very hard. And in industrial scale, we need to clean rooms, the chambers, the closed chambers. We need to sensors for detect of these changes. So, mostly, I speak about flat sheet, but we can produce the hollow fiber membranes also. The time is finished. 1 hour is finished. But my slide is this number. I speak 10 minutes and continue in lecture 5. Okay, Prof. Rakab? In the fabrication of hollow fiber membranes, instead of applicator in flat sheet, we have a spinneret. We have a spinneret. A spinneret acts as a applicator, Dr. blade in flat sheet. In spinneret, this is the actual picture. We have this structure. You see, when we open this device, the spinneret have different sections that you see a needle. This better shows. This is the spinneret. We have a polymer solution inject to this needle, okay? But we want to produce hollow fiber, tube, not fiber. In production of fiber, we have not this central tube. We have only this needle. But we want to produce a tube. And for this purpose, we used a non-solvent in the spinneret. And we first coagulation inside of the spinneret. Okay? We have inject this solution from here, but as injected in this place will be contacted with non-solvent, and we have solidification here inside of the tubes. This water, this bore fluid, we say bore fluid. Bore fluid will be inserted in the spinneret inside of the tube. And after the production of the tube, directly go to the coagulation bath, and the other process is similar to the flat sheet. We have a coagulation bath, non-solvent, and we have a washing bath and take-off roll. Okay? Therefore, inside of the spinneret, we have a bore fluid that usually is water, or water containing NaOH, caustic water, that this NaOH increase the solidification. And after production, we take off on the roll. Therefore, we produce the tubular hollow fiber that have entrance and exit area. Usually say to the inside of the hollow fiber, lumen area. Lumen area, that means the inside of the hollow fibers. And we have a selective layer. In the flat sheet, we say that top layer is selective layer and bottom is support. With control of conditions, we can produce the selective layer inside or outside of the membrane. With control of bore fluid conditions or coagulation bath conditions, we can produce the selective layer inside or outside. Okay? Based on this control of conditions, the feed can be in outside to in, out to in, here, outside in, or inside out. The feed can be inside of the tubes, or the feed can be the outside of the feeds, based on the selective layer. Thank you for this lecture. If you have questions. Yes.
Is in the non-solvent induced phase inversion technique, is the solvent affecting the choice of the solvent affecting the property of the membrane, obtained at the end?
Yes, yes. With change of the solvent, polymer solvent, the properties of the membrane can be changed, and the solvent is very important because with change of the solvent, the chemistry of the liquid solution can be changed. Okay? As you see in this slide, every parameters is similar, only the solvent changed from dimethylformamide to a methylpyrrolidone. With change of the solvent, the chemistry change, the viscosity of the solution change. For example, in DMSO solvent, we have very viscous solution. In NMP, we have a low viscous solution. As you see in this slide, with change of only the solvent, the morphology of the membrane changed from finger-like to the macrovoid structure. Okay, the solvent is very important because that influence on the exchange rate.
Okay, thank you.
If I want to prepare a composite membrane,
Yes.
then how to add?
Yes. I will discuss about nanocomposite membranes in the tomorrow section about composite. For fabrication of the composite membranes, we have a different method. The simple method that we add nanoparticles to the solvent, and for good dispersion, we use ultrasonic radiation. Ultrasonic good disperse the nanoparticle, and after good dispersion, we add polymer and let to dissolve complete. It is the simplest method, but we can add a coating layer, we can spray the nanoparticles, and different methods.
Thank you.
I will discuss tomorrow.
Can it be possible that in case of a Dr. Blade method, coating that we're doing,
Yes?
and goes on adding the different
Layer?
layers?
2 layers, yes, yes. We have devices that coat 2 layers continuously. Between the first Dr. Blade and second Dr. Blade, we have a 5-6 centimeter distance. First 1 layer coat and next second layer. We called dual layer membranes. In the preparation, and in some cases after the preparation of the first layer and drying, we can use the membrane as a support, and second layer will be cast on the solid first layer. There are many methods for production of the dual layer, 3 layers from polymers. Ceramic layers, ceramic polymer membranes have 3 or 4 layers, but UF, MF membranes usually is 1 layer. But some Nafion membranes have 2 layers. When we see the cross-section of Nafion membrane, we see it is 2 layers. Our RO membranes have 2 layers, 1 thin layer and 1 thick layer. But we have dual layer, have 2 different polymers can be coated.
So how one can be assured about the binding of 2 layers if it is being formed?
When we cast the second layer, for example, on solid polymer, the solvent of the second layer can be dissolve the support layer and produce an adhesive. And this causes to increase the stability. Okay? So because the solvent can be dissolve the support layer, and this dissolving act as a adhesive. All of adhesive is a polymer and a solvent. And this solution can attach to the many surface.
Sir, actually I have used YSZ, yttrium stabilized zirconia. Over that I have casted nickel oxide. But I faced that my tapes were broken. There were cracks over the tapes. So
And then repeat your question.
yttrium stabilized zirconia was the main support over
Yes.
which I casted nickel oxide.
Yes.
So, but the way you are saying, no, over another we have to cast. But I have seen that there were some cracks over the nickel oxide. My tapes were spoiled.
For cracks in the membranes, we have a different methods for reducing of the cracks. The defect or cracks cause to reduce the membrane performance. In gas separation, for example, use polydimethyl siloxane as a defect filling layer. Okay? When we produce polyimide gas separation membrane, maybe because the polyimide have a semicrystalline, maybe we have a defect. In this case, we use the sealing agent.
Yeah, see.
Sealing agent for filling the cracks. For ceramic membranes, for reducing of the sealing, we use very, very fine powder. When we have a big pores, big defects, with using of a thin layer of the very fine powder as a force layer, we seal these cracks. Okay? And mostly named as protective layer. We also, in fabrication of most TFC membranes for gas separation and RO, after preparation of membrane, we coat a protective layer on the membrane surface for reducing the defect in modulation. When we module and produce the envelope, maybe the surface of the membrane can be harshed and can be defect. Okay? Therefore, we use a water-soluble protective layer on the surface of RO membranes, for example, polyvinyl alcohol. And when we produce the module, during the test of the modules, the polyvinyl alcohol will be dissolved in water, and after 2 days, 3 days, this layer completely removed. Therefore, the sealing is very important in the membranes. Okay? No question? Thank you.
Thank you. Thank you so much for your lovely talk. And it is really a very visually attractive and very informative. And I think our audience has benefited a lot from the insights that you have provided. And I can see from the interaction that happened after this that they are really interested and they have really learned a lot. So now what we will do is that we will proceed for a short tea break. After that, we will be joining here in the in this same room at after 5 minutes, after 10 minutes. Okay. So just one announcement is that after this talk, there will be a hydrogen energy level talk for 1 hour, and after that there will be another lecture followed by Professor Bhatanpur. Okay. Thank you. So 312 for the tea.